We can see the slides and we can see you. I think we're good.
Good, perfect. So again, this is work. So the idea here is to give you some introduction into the work that's been happening, starting in Michigan with Emmanuel, also with Sergey. Ja, I think, is no longer here, and Hiroshi in Japan, and Anna Kauch in Vienna. And the idea, or sort of the raison d'etre of this whole talk is, well, I will be talking about response functions. And that's our main thing we use. In many-body theory, we cannot, I mean, some people are audacious enough to model the whole wave function. We are usually content with understanding the 1- and 2-particle propagators. And so in general, I will be focusing on this 1-particle propagator. I have some slides for the 2-particle one, but I'd actually be very disappointed if I get to those, because it means that you haven't asked any questions, which I encourage you very much to do. I already know this stuff. Emmanuel also already knows this stuff. So feel free to ask me questions. And if we veer off on some tangent, that's perfectly fine. Okay, so 1- or 2-particle response functions. 1-particle response function just says we have a starting point and an end point, and a average, the movement of the average particle between those. And this is basically some non-interacting contribution, and then some vertex encoding all the interaction with the system. And the same is true for the 2-particle Green's function, which is composed of 2 particles not affecting each other much or at all, plus some effective interaction with the system encoding in this vertex here. So why are those objects interesting? Well, the 1-particle response is interesting because it's connected to the spectral function, so the population and the excitations that you have, 1-particle excitations you have in your system, and you can measure those in some way with photoemission spectroscopy or inverse photoemission spectroscopy. And the 2-particle response is, in a sense, it's also very interesting. It's connected to susceptibilities, so responses of your function to some more complicated perturbation. And it's also accessible experimentally. You can do RIGS, you can do NMR, and you can do neutron, and all sorts of spectroscopic methods that give you those. Right, that's why we care about these objects on their own. There is a theoretical reason why we also care about these objects, and these are so-called self-consistent field theories. And so these self-consistent field theories, they come in 2 variations, again in a 1-particle and a 2-particle variation. And that self-consistent field in the 1-particle case is what's called the self-energy. And that's usually the level where at the 1-particle level, we will make approximations. So maybe the most well-known self-consistent field approximation is Hartree-Fock, where we approximate that self-energy by the Hartree of the Fock diagram. There are others like DMFT, where we say this self-energy is local. And then there are a bunch of other things where we can make extensions to that. Now, how do we connect the self-energy with that propagator? Well, out that self-consistent field, we have a diagrammatic equation that does that for us. And that is the Dyson equation, which you're probably all familiar with. And the same is true for the 2-particle case. Also there we have a self-consistent field. The situation there is a little bit more complicated, but in the simplest case, we can say that self-consistent field is what's called the irreducible vertex, and we will denote that by gamma. And there are also a bunch of approximations we can make at this point. Maybe the most interesting one is the random phase approximation, which is used all the time, but there are others. Then there is like d gamma A, which is sort of a 2-particle extension of this DMFT idea. And there are other ideas where you can approximate that vertex somehow. Flex is another. And again, we have an equation that connects these irreducible channels to the full set of scattering channels. And that equation is called the Bethe-Salpeter equation, but it's in principle just the 2-particle version of the Dyson equation. We just build this up this layer. All right, so that's why these things are interesting. So what's the problem with doing that in practice? Well, the problem is that these Green's function, these propagators have these wave-like qualities. They're resonance, they have resonance structure, which means the underlying spectral function is very, very spiky for real systems, very complicated. And that makes it very hard to do, first of all, to model this object, and it makes it very hard to solve self-consistent field equations with that object. And so what we do is we take a hint from high energy physics, and we move to imaginary time, or imaginary frequency axis, where all of these functions are very nicely behaved because they are mediated by a Laplace or something like a Laplace transform. And if you remember, the Laplace transform doesn't have this nasty I, it just has an exponential function. So the Green's function is just in the sum of these exponentials, which is quite nice to work with. So everything cool, right? So we have now a very smooth approximation. Well, is it though? And it turns out if you ever worked with these imaginary time representations, they look very nice, but there is a issue that you will have to face with, and that is how do you discretize this imaginary time grid? And the simplest thing you can do is just take equally spaced points here. But the problem with that is since there are exponentials here, exponentials decay very quickly, and most of its structure of these exponentials are sort of confined to these borders, because that's where you have the strongest change in these functions. So most of what's going on in this function is actually here at the borders. And here they're reasonably nicely behaved. As you can see here, you have 2 orders of magnitude, and then here, there not much is going on. So, okay, good. So the time grid is maybe more complicated. Okay, let's go to frequencies. Well, there you have another problem, which is sort of the inverse of that problem. If you have something on short time scales, you have something is going on long frequency scales. And that's exactly what's going on here. It turns out that the propagator, if you expand it in frequencies, is very long range behavior. That means if you want to model it in frequency, you need a lot of frequencies. In fact, you in principle need infinitely many of those, because there is a jump here that this signal jumps in time. So that you can cure by attaching some analytic form that you know. But still, even if you do that, you need very many frequencies often. Or do you? I mean, so that's what you typically do or the standard method that we use right now is usually a dense grid with tails. So we do what I said we did. We have a discretization here that is just equal discretization. So we take a bunch of points equally spaced, and we attach some model that models this long range behavior. So, and if we think about this, what is the error that we are making here? If we take n of these points, it turns out if we take the inverse temperature beta, and W is the bandwidth, and epsilon is the error we are making, or we are allowed to make, say, then the number of points we will need scales linearly in inverse temperature, linearly in the bandwidth, and linearly in that accuracy, in the simplest case, or with some power in that accuracy, depending on how good our model is. So an improvement has been suggested to use orthogonal polynomials here, which, since these are smooth functions, that's a nice idea in principle. And then, since it's a smooth function, mathematics tells you that the error drops in principle very quickly with but we still have that problem that these, as we increase the bandwidth or decrease the temperature, these features get sharper and sharper. So we still need a lot of a lot of these points because the scaling is still not very good. So this is usually the point where some people say, well, I never had any problems. It works for me. And my answer to that is, does it though? Because if it does, chances are what you're doing is calculation at moderate temperature. You're mostly doing one particle calculation, and you're mostly doing model calculations. So you already have condensed down your full Hamiltonian that spans several part rates of energy down to a model which has only a couple of EV, say, or even smaller of energies that you need to consider. But if you don't do that, for instance, if you want to do quantum chemistry, well, the bandwidths become very large. And then, well, this W blows up, which blows up, remember, your grid size. Or if you want to model things like superconductivity, where you need to get down to very low temperatures, well, then the bandwidth in units of temperature becomes very large. Or if you want to have reliable data on the real frequency axis, you have to invert that transformation, and that works better if you have more data. So there you need, this thing becomes 10 to the minus 16 often, if you want it, or very small. Anyway, you need a lot of frequencies. And then compounded by the fact is if you do two particle calculations, you need a discretization in each of these axes, which means that that problem, you have that problem to the power of the number of particles, or even worse, the number of points that you have in your system. And if you do diagrammatic equations, you can do them in the frequency representations. They're cheap. But then you're again in this frequency representation. If you want to do them in the polynomials, they're not diagonal anymore. So you again have worse scaling. So that's sort of the problem that we're facing. Is that somehow clear? Is there any question there?
Yeah, maybe a comment, right? I mean, if you go to calculations that people were doing in the Matsumoto or imaginary time formulas, at least if you think of the Monte Carlo field, that typically the algorithms that people had would scale in the number of time slices that you have, you know, at least cubic. Well, you know, sometimes quadratically, but when you look at it carefully, they're typically cubic in the number of time slices. So there was never, in the QMC field, there was never, a need to very many, to billions of time slices. It was just not an option. You would be dead in the water at 100 time slices, maybe at 200 time slices. And so there's a different field in FRG and sort of analytic diagrammatics where these problems appear a little bit more prominent, but there you typically are limited by the size of your vertices and the number of frequencies that your vertices have. So you're also limited to basically 100 frequencies in each direction. And so I guess one of the reasons why these things became important a couple of years ago when we started working on this, because we were having these GW and GW and other types of imaginary time formalisms, where all of a sudden basically you could go to many more frequencies, and so these problems started to show up, and also the frequencies, because we were interested in started to be ridiculously large. So it was really sort of a paradigm shift to new systems that necessitated development of all of this stuff.
Agreed. That's the other. Sometimes you had, I mean, with these continuous time algorithms, I would say the time slice problem goes away to a certain extent, but you're absolutely right. That's an issue. And I think you just couldn't also, you didn't have the computing power to do like fully self-consistent GW. You just couldn't. I mean, that's, yeah. All right, any other questions? Or is that somehow clear? Anyway, so what do we need? We need a representation on your imaginary time axis that is controlled. That means that we understand its error. It should be compact because we don't want to store or work with many coefficients. It should be fast if we do like diagrammatic equations, which remember we have to do in all these self-consistent field theories. And ideally, we want that in the 1 particle level and the 2 particle level. So that would be my outline. And probably we won't go to the 2 particle level for now, but again, let's see how far we get here. So let's start with the controlled and compact representation. And there I want to introduce you to a decomposition which you may not know. You probably are aware of an eigen decomposition where you have your square matrix and you get your eigenvalues and eigenvectors. But it turns out there is a generalization of this to arbitrarily sized matrices. It turns out this is called the singular value decomposition. It's very important in density matrix renormalization group and becomes more prominent also in many other fields now. And instead of, remember, the eigen decomposition would be you have a matrix and you decompose it into a unitary matrix, a diagonal matrix, and then the inverse of the same unitary matrix. The difference in the singular value decomposition is now that this matrix here is different than the first one. So you have 2 different unitary matrices here. So, and you can write that in terms of these unitary vectors. So that's there again, like a set of projections scaled by what's called a singular value. These singular values, you order them. This is the largest singular value you call S0, and then they become smaller and smaller and smaller, and they're all positive or non-negative, I should say. So you order them by magnitude and they're non-negative. So this is a bit different than the eigen decomposition where they might be negative, but you can always absorb that sign into one of those decompositions if you do it. And that's why you in practice are here. So these vectors form, as in the eigen decomposition of a square matrix or a Hermitian matrix, form orthogonal bases. So we can understand then an arbitrary matrix as a rotation or a unitary transformation, so some basis rotation. Then we scale that rotated object by some factors, and then we rotate it back. But we rotate it back with a different transformation. So that's for matrices. And now crucially, and that is what drives most of these ideas, is that you can show that in for a specific sense of best, you can find the best low rank approximation by just throwing the smallest singular values away, right? So you truncate this sum to the largest singular values, and that gives you, in a sense, the best low rank approximation to that matrix. So you reduce the data that is in there. So that's crucial. Is that sort of clear what's going on here? Because now we are going to generalize, or maybe let me, any questions here? Okay, because now we're going to extend that to that kernel we had before. So remember that also looks a little bit like a matrix vector equation multiplication, but it's a integral here. So that thing is a function of 2 variables, and it's a Fredholm equation of the first kind, if you want to know, but it's basically a matrix vector equation. So as with before, we can now decompose this thing into 3 parts. A set of functions, remember these are not indices, these are functions on the imaginary time axis, times a set of singular values, times a set of functions on the real axis. So I've plotted and this sum now extends to infinity because this is a infinitely large space. And I've plotted the low-level functions here. So you see that this dark blue line is the first or 0th u, and then you have the first that has one node, and the second has 2 nodes, and so on. And then we have these functions here on V that are sort of clustered around the origin. We'll get to that point. But the crucial point here is these singular values. So what you see is that, and that is a generic feature of these sorts of kernels, is that these singular values decay very, very quickly. So in other words, you have here 10 to the 0, and here you have 10 to the 12 in 30 or 35 singular values. So they decay very quickly. And remember that what I didn't tell you is that the error we're making here is proportional to the largest singular value we throw away. So in other words, we can approximate that kernel very well by already taking like the largest 30 singular values. So this is a good approximation to that kernel.
Markus?
Yes.
So you have Otsuki down there, and basically Hiroshi Shimoka's work for the singular value decomposition.
Pardon, can you, sorry, I didn't hear that.
Your reference for that?
Yes.
Is the Otsuki, I think this is Hiroshi's work.
Yes.
For the IR. This decomposition is actually in any maximum entropy code. So it's much older. I think it's actually from Beach in like early 90s.
Yeah.
So that's been all over the place. Back when we were doing entropy continuations, it was much easier to do that by reducing the degree of freedom.
Yes.
So you essentially, go from hundreds of degrees of freedom for fitting your Matsubara data, like typically like 10 or 12 or whatever. And so you would optimize the data that you have within those basis functions that are very compact. And that's actually important to know when if you're having massive entropy and you're observing oscillations at high frequency, sort of wiggles that are showing up at higher frequency. Very often these wiggles just come from the basis functions that you have available because you've truncated yourself to 12 or so basis functions. At high frequency, you're going to see basically what those basis functions look like on the real axis. You're not having a complete basis anymore. And I've seen physics results interpreted out of wiggles at high frequency that really come from this truncation. So yes. Know that if you're running maxent, there is this singular value decomposition underneath it. And when you're analyzing high frequency features, you have to be very careful that you have enough basis functions to actually capture what's going on. Typically, you don't.
It's a very good point. So I should put that reference there. That's absolutely right. I also discovered this on the wigglers of the real frequency axis. There is actually, I don't know if you know this paper. There's someone who analyzed this, and I can actually, if you like, make a comment on that. This is very interesting because if you now put that, so what you can do now in practice is put that decomposition. So that's what the maxent people also did essentially for a different reason, it turns out. But what you can do is you take this decomposition and you plug it in here. So this thing, I've written it now in frequency, it doesn't matter much. What you find is that you get simply a coefficient that comes with projection. So you rotate it into the singular basis. That means projecting this row onto these basis functions. Then you scale it with that thing, again, like in the matrix case, and then you rotate it back with a set of basis functions. So, and now what turns out that you can, part of it you can show analytically, part of it you can show numerically, is you find that the singular values decay, and we showed this before, as the exponentially fast. And with the scaling, so that depends on your bandwidth and your temperature, but only very mildly, only logarithmically. So that means if you double your bandwidth, you get a constant number of additional basis function, but it doesn't blow up by a factor. That's the point. So it decays very quickly, and it still decays very quickly if you increase that factor, which is a good thing, because remember that's a problem for. So, and the other thing we in principle also need to prove is that these things do not grow arbitrarily. So they at least go as a constant. However, they do not decay necessarily. And that is the problem that has plagued some mix-end algorithms very strongly. Because what they said was, well, we have this kernel, let's truncate it here because we know we have the singular values that decay. But the singular values only make a statement about the imaginary axis of the problem. They do not make any statement about the real axis. That means these coefficients do not decay. That means a low rank approximation where you assume that this function is expandable in these coefficients is wrong. And this has been in countless codes, and it took a long time for people to realize that. So what you can still use the kernel and you can still use the low rank decomposition, but you have to confine yourself to the imaginary time axis. And that is, there is a couple of papers that go into this direction. But however, on the imaginary time axis, what happens is that these singular values, together with the fact that these coefficients do not blow up, mean that taking this as an expansion coefficient, GL, this whole thing, means that these are guaranteed to decay because they decay at least as quickly as the singular values, because that's the prefactor here. So, but this is nothing that a set of basis functions. That means that we can expand the Prince function we have here in these basis functions, and we can be sure that the expansion coefficients we write in front of them decay because they are guaranteed to decay by virtue of this singular values. So that's maybe the crucial point I want to make. So any questions, I appreciate it here.
Your paper in preparation with Hiroshi, what's it going to be about?
About that actually has come out. That was to prove that this decays exponentially.
Oh, very nice. So I'm not sure of that one. You got to send it my way.
Yeah, it's in the appendix of this. You actually co-author. It's in the appendix of the appendix of this lecture note.
Oh, that one, the translation of the Japanese lecture note.
Yeah, yes, I put it in the appendix of that. That okay. You can actually show that these two properties you can show.
Okay.
I show you where it's done. And it's part of it is also in this beta paper actually. But we, okay. Any other questions? Don't be shy. Okay. All right. So that's maybe the important formula here. So what's going on here? So people who have worked in our field for a long time know that there is in quantum many-body physics, there is something called the no free lunch theorem, which means the difficulty is always conserved. And if you find a very, very nice thing going on, it usually means that, yeah, there's something that becomes more difficult at the same time. And the point here is the way to think about this kernel and this basis is that what people knew a long time from maximum entropy is that as we transition from the real to the imaginary axis, these things become smooth. In other words, think about like a blurring filter. That means we lose information. Or in other words, we lose numerical information. We lose numerical significance, to be very precise. So that means we have less information available in the imaginary axis than we have on the real axis. However, since we have less information on the imaginary axis, we don't need to store all that information. So we can compress the data. So these are the two sides, right? We have information loss, and that allows compression. And that really is what these singular values tell you. The stronger these decay, the more we smear it out, the more we lose, the stronger we can compress. That's the point. And in the end, what that means is we have a basis for the imaginary time and imaginary frequency axis, a representation where if we truncate it to the L most significant, coefficients, the error term we are making is proportional to the, or is decays at least as quickly as the singular values. And that means that the number of coefficients we need is logarithmic in the bandwidth in units of temperature and is also logarithmic in the error. That's the crucial statement we are making. And that allows, that in practice means that you never need more than 200 coefficients for any system I can think of. Right, so we've solved the first two problems. We have a thing that is compact, and we have something that is also controlled. We know a priori how large our error can possibly be because we know the singular values, and we know that asymptotically, we cannot exceed those. That means our singular values here already tell us how large our error can be. And now that's very useful because sometimes we know, okay, our Monte Carlo error is in the 4th digit. So we don't need more coefficients, that we don't need 16 digits of accuracy, because we know, okay, that doesn't make sense because everything below the 4th digit will be noise anyway. That's very useful. And we know that this L is also compact. All right. So, but now we come to the fast part. And now let me go back to the self-consistent field equations we talked before. We said we had the self-consistent field and some approximation there, and then we had a way to go back to the full response function, the full propagator. And typically we solve two equations. That's what's called self-consistent. We solve them sort of until they agree with each other. And one of them is this Dyson equation, where we dress the propagators with the self-energy we have plugged in. And that equation is diagonal in frequency. And then we have to figure out that self-energy. And usually that is some diagrammatic equation, either Hartree-Fock, where we truncate it to first order, or GF2, where we truncate it to second order, or GW, or any other method. We have some functional that only has a skeleton series, because otherwise this equation doesn't work. It's called the Luttinger-Ward functional. And we derive that by the propagator and we get self-energy. The point I'm trying to make here is that typically this interaction for the systems we are considering it is mostly time local. Doesn't have to be, but the most significant contribution is often time local. That means this equation very often is better to solve in time or imaginary time, and this in frequency. Note that nowhere I have this nice basis expansion. Ideally, I would like to solve them in this basis expansion, but it's time and frequency here. If an equation is diagonal in one of these bases, it's usually very off diagonal in another basis. And it turns out both of these equations are heavily off diagonal in the IR basis and cost about L cubed time to solve. And that's bad. That we don't want. Right. Or this equation costs L cubed to solve, I should say. This equation may be significantly worse, actually. So how do we do that now? So ideally, what we want is, we would like to solve this equation in frequency and this equation in time, but keep in mind this nice basis we have, this IR basis. And in practice, we know how to do that, right? Why do we know how to do that? We know it maybe not for the IR basis functions, but we know how to do that with polynomials. Because with polynomials, we always have a set of function, and we can expand any function, any smooth function in these polynomials. But we also have a Gauss quadrature rule, which means we have a set of nodes where we can evaluate that function and then reconstruct the coefficients from these. So to every set of orthogonal polynomials, there's a Gauss rule that allows you to do integrals with those polynomials and reconstruct the functions. And for polynomials, these are always the zeros of the highest order polynomial. It should be a big L here. So the zeros of the highest order polynomial that you're or the highest plus one order polynomial that you're considering always gives you the nodes on which you should evaluate your functions. So we have now a set of times, and this set of times are precisely the nodes of the highest order basis function. So evaluating is easy. We just need to evaluate the function at these time points. This is just some object here. And the fitting just tells you there is a set of weights and a set of times. It's just Gauss quadrature. And you do that quadrature and you make some error. And you can show that for Chebyshev polynomials, these two errors are actually consistent with each other. So that means we have now a way to go from time, from the coefficients to time. Okay, that's trivial, but also to go back. And we don't need many time points. And it turns out there is a similar thing for frequency. And the reason is that the Chebyshev polynomials are also polynomials in 1 over the frequency. If you take the Fourier transform. So that means you can do the same trick. You can construct a set of frequencies and you can evaluate that object in frequency from the coefficient. You just evaluate the Fourier transform. You take the Fourier transform of the Chebyshev polynomial and you can evaluate it in frequency. And you can also go back. You can take that polynomial and do that, get the coefficient by just taking this set of frequencies with a set of weights. So and that in principle solves our problems. It allows us to go from time to frequency just by going through these matrices. We have a set of matrices that get us from time to Gauss integration, gives us the coefficients, and then some evaluation gives us the frequency, and then we can go back. So that's the crucial thing now. We have a way to transition between the two for polynomials. And now it turns out that the basis functions of that kernel, we are very, very lucky because the basis functions of that kernel behave similarly to polynomials. I would like to say that we figured this out before we tried. We didn't. It turned out that it worked. And then we found some paper by a Russian or a 500-page book by a Russian person who explained why it works, written somewhere in the end of the 60s, where he said, this is guaranteed to work for kernels that have a certain property that these kernels that we are considering have. So in other words, we can do this not only for polynomials, also for our IR basis functions. We have a way to go from time to frequency. And that means we can solve each of these equations in the basis they're best suited in. Right, yes.
So you say basis of K behaves similar to polynomials. In what sense do they behave dissimilar then?
Yes, so in the following sense, they have, this basis function always have the nth basis or lth basis function has L roots, which is nice because that's what you need for these sampling points. It turns out they have a Gauss quadrature. They have something called an extended Gauss quadrature. So it turns out you cannot only construct quadrature rules for polynomials, you can also construct them for basis function of kernels of this form. That was very super because that's exactly what we need. So what that amounts to is that we can, in principle, have that correspondence. That's what we figured out. Yeah, there is this fight again by Samuel Kalin. There's this book, and there's some other Chebyshev did some work on this, and it's basically impregnable, the book, but it's yeah, it has the theorems in there. Any other questions?
No, maybe a quick comment. So if you look at these equations, they're all order L squared.
Yes.
So transferring back and forth is basically order L squared. You can do a little bit better for the Chebyshev nodes to coefficient with the fast cosine transform. We never actually did that because we also then go, to 350, and it just wasn't ever worth it.
Yes. So exactly, you can, for Chebyshev, you can do L log L, I think, right? If I remember correctly.
Legendre, I think, or there's something similar, but I don't remember the details.
Yeah, in practice, that's also a good comment. L squared is enough because you need so few coefficients. Yeah. So if you, for Chebyshev, that I think would probably even make sense. In practice, if you have 200, you don't really care about 200 squared here. Not really.
And so when you look at this stuff, by the time we had the Chebyshev, the transforms just simply disappeared from the profiles. They were just not a consideration anymore. Just other parts of the code. Before we had, there were earlier attempts at doing, more compact squares, right? So there was one with spline that really worked. There was another one that came out of a GW, wave boost group, where they had power grids that were essentially linear grids that were linear on sections of the imaginary axis, where those sections were then distributed in a logarithmic fashion. So they were power grids, and so this is how we started with the thing. And either this line nor the power grids actually really work.
Yes, power grids, so small comments that they actually behave as just regular equally distributed grids.
That's right.
So the thing was basically the same as for the group.
Yeah. But of course, we didn't know when we started with this. And the other thing is the Legendre that you also mentioned. So historically, if you look at, the Legendre, that was done basically to enable better measurements in continuous time Monte Carlo codes. And when we started looking at these grids, we didn't care about QMC at that time. We basically cared about how to better resolve this exponential decay at the beginning. And it turns out that, Chebyshev is marginally better than Legendre. You would never, switch to Chebyshev if you already have it. IR is actually quite a bit better at resolving this. And we'll have to see how, Olivier and Jason Kay's newest version of this is essentially a bunch of delta poles for approximating an imaginary function, how that behaves. I think it'll be interesting.
Yeah, that's. I mean, the two approaches are extremely closely related. So they call it the discrete Lehmann representation, because they rely on essentially the same truncation. So usually, when you do a singular value decomposition, a truncated singular value decomposition, you first do what's called a rank revealing QR decomposition. And then you take that additional factor R and you diagonalize it by applying another matrix from the other side. And what they did, basically, they stopped after the first step. So the properties that you get essentially are pretty much the same. So I would expect the performance to be very, very similar, though it's slightly less compact and it's not orthogonal. And they say, okay, it's not a problem, but I'm not quite so sure. But because non-orthogonality can be an issue in diagrammatic calculation. So I'm not yet convinced 100% that non-orthogonality is as benign as they say they are, but I would have to see, play around it with myself.
The other out there is that the vast groups of Presley, they basically also have an approximation of Matsubara data as a sequence of exponential poles that decay.
Yeah, that is actually very interesting because it maximizes a different norm. So I would be actually very intrigued to try that, because the two approaches, DLR and DIR basis, are similar in the sense that what they are, this notion of the best approximation is a two-norm sense, whereas the Kalter Kongresse there is a infinity norm sense there, which is interesting in a couple of respects. So I'd be actually very interested how the two approaches compare.
There's a bunch of approaches out there that are not the uniform grade that everybody used to work in. I think we're still in a process. One should actually. But there's been a lot of progress in the last, I would say, 5 years or so. That just really allowed you to get to much larger systems, much lower temperatures, and actually have, you know, good control over what you're doing.
Yeah, I agree. Yeah. Anyway, how do you? Again, what you see here is basically from this paper that when you choose, I mean, in practice, you can choose either the sampling points as the nodes of the Elf basis function. What we do in practice is we choose it according to the maxima of the L minus first basis functions. Now that is quite similar because of a property these basis functions have called strong interleaving. So, and it allows us to calculate one basis function less, so that's always quite nice. And so you can switch that out for the roots and of the next basis function, and you get a very similar picture. But what you see is, if you look at these points, is they're very strongly clustered towards -1 or towards 0 and beta. And remember, that's when we say that's where the magic happens, right? That's where they so they understand in a way that this is a propagator and I have to look at these points more strongly. And that's precisely what goes on here. And we see that it's very easy to get good errors. Then you see that the error across the spectrum then is very small, 10 to the -12. And you have a similar picture in the Matsubara frequency axis, where you also see that this is a log scale, so it's a bit hard to see, but you see that you have one cluster of frequencies at low frequencies where also interesting thing happen. And then you have many frequencies that extend outward to very high frequencies. And that again is indicative of the fact that that's where some of the behaviors are very long ranged. So you need the frequencies out there. But that's sort of implied by the fact that we constructed it from the kernel. So we understand how such a propagator looks like. So,
I have a question.
Yes.
So, as far as I know, also from my experience on using the IR basis, on the multiple frequency, we have the sparse sampling both on positive and negative frequency point. But but you also have the symmetry between, like for object in the frequency between positive and negative frequency points. So does that mean additional symmetry that we can explore, that we can actually reduce the point by half, or?
You could.
Ever to have negative Matsubara frequencies.
Yeah, I mean, but if I just use half of the sparse sampling point in this IR representation, I imagine I will get different result, right?
No, because you have complex numbers on the Matsubara frequency, right? So you have L points in sparse sampling, right? And you have L over 2 points in Matsubara, but you have real and imaginary points. That's where the information goes.
Yeah. We don't need both. Even in IRBs, we still don't need both of those positive and negative frequency point, right?
You never need the negative Matsubara frequencies.
So then the idea, like the rough, like quantitative idea, like having, once you have similar information on imaginary time and frequency point, does that mean I actually, like the imaginary time sampling could actually also got reduced by half?
No. No, because in the imaginary time sampling, you only have real numbers.
Oh, okay.
Right? You have 1 degree of freedom on the imaginary axis.
Yes.
No, you don't.
No. For our calculation, you don't. For our calculation, everything is complex.
For calculation,
yes, for the GW and GF2, in the K phase,
yeah, that's
all
right.
your information is complex.
Yes. Yes. So that's the reason why in practice you could. You're absolutely right, because the Green's function is real, but that is something that you do not explicitly use in your IR basis. You do not enforce the realness of the Green's function. You could, and then you could do exactly what you said, that you could reduce the number of frequencies by 1/2 and enforce the realness of the frequency.
What I'm saying is that when you're doing this in a periodic system and you're having a case-based calculation, the imaginary time, there are cases where the imaginary function is right, and so that's right, symmetry or positive and negative.
Yeah, then you need both. Yeah. Yeah. I mean, there is another way to skin this cat. Probably you could say, well, the problem is that I didn't actually enforce anything on. So the reason why this kernel doesn't understand anything here is because I didn't actually enforce any constraints on this spectral density, right? It doesn't understand that this can only be, I don't know, non-negative and whatnot, right? So that's why the IR basis doesn't understand this either. Right. So putting this all together, we said we had to solve these two equations, like a diagrammatic equation for the self-energy and then another diagrammatic equation for addressing the propagators. And now how do we connect that? Well, we do it using these two translation procedures. We base it on our IR basis or another basis. We take the Green's function, we compute, we take the self-energies, or say we take the Green's function that we have expanded, we transfer it to time on these special points, we solve the diagrammatic equation for the self-energy at these time coordinates. This should be a sigma, I'm sorry. So this gives us the sigma. Then we go back and try to understand the sigma, the expansion coefficients by fitting. And then we expand again the self-energy on this basis, on the self-energy on frequencies. One has to be a little careful there with the spontaneous term. And then we solve the Dyson equation on these sets of frequencies. We have the Green's function on the frequencies, we fit them again, and we close that loop. So, and that allows us, since these procedures are now L squared, this is typically a procedure that is more expensive, L to the 5 or so, or no, I mean, it can be L actually. For the simplest case, this is actually linear in L, might be L2, L3, it depends on the complexity here. And this is also L, so these translations are a bit more complicated, but typically actually there is a matrix inverse there which dwarfs this guy. So for more than one orbital, and this will strongly scale with orbitals, and this will strongly scale with orbitals, and these will not matter much. So this is the way we are going to do this, and thus we have solved sort of the third problem, that we need fast diagrammatics. And so from this paper, you can see that can very quickly, by this sort of procedure, converge energies to very high levels. That wasn't really possible before, actually. You would need millions of Matz-Bar frequencies to do this properly, because these are like noble gases, and noble gases have this very deep lying core state. So you have this problem that your bandwidth is very large. All right. I think I'm out of time. I don't know how much time I have.
Yeah. probably have an operational comment for people using the IR basis. So you have the parameter lambda there, right? And lambda basically characterizes the bandwidth of your prompt. If you manage to choose lambda too large, then you're going to need more basis functions to converge your system, and the thing is going to slow down a little bit. That's, you know, whatever. So if you manage to choose lambda too small, then the whole thing becomes unstable. So be very careful with that parameter lambda up there, and make sure that the lambda that you choose actually captures the bandwidth of your system. And, you know, conversely, if you find that your simulation blows up for, you know, for random reasons, choosing the lambda wrong may be one of the reasons, and so that's always a good thing to check.
Right. Very good. Because if your lambda is too small, you break one of the assumptions here, which is this one here, basically. And that means that this does not decay properly, and it means that this one can then blow up. And
so to my mind, this is the major drawback of the basis. If you screw up lambda, your calculation is going to blow up, but you're not going to get anything sensible. But if you don't know where to look for it, you know, that's a catastrophic failure of your simulation. Yeah, no, I think you're absolutely right. So this you have to check. To my mind, it's easier to choose lambda. So the bandwidth in units of temperature, I have a maybe more of an idea of what I need than by choosing the number of Chebyshev polynomials. But of course, you can also translate that into some other criterion. So it's tomatoes. You have to choose that value. You have to have some upper bound of your bandwidth, interacting bandwidth in units of temperature. One comment though, choosing it too large is not a huge problem, simply because this doesn't grow that quickly with beta omega. So for instance, choosing it a factor of 10 too large means you have 20 additional, or 25 additional basis functions. So if you have 100 before, then you have 125. So it's not the end of the world, unless you're very short on CPU time. That's right. So a typical case how this goes wrong is you do a calculation for, you know, an atom with an atom that is somewhere in the upper part of the periodic table, and then you replace it with an atom that is somewhere, you know, the same row, but just, you know, sorry, same column, but a little taller. And so that basically go down, like the energy between them. And that's more frequency. So just keep that.
Yeah.
Sort of that IR is foolproof.
I would maybe, I don't know. So this concludes the one particle thing. I don't think I have time for the two particle stuff. I would maybe, if there's still a little bit of time, just show you how this works in practice, and do one short code example, or are we out of time completely?
Markus, I have a better idea. I think the two particle stuff deserves its own talk. Will you be willing to give that at a later point?
Yeah, sure. That we can do. Should I still quickly show the library, or do you think we make a cut here?
Let's cut it here, and let's do the two particle as its own, you know, complete set.
Okay, that's fine. Then I would just invite you to. We have a new library out there that I will just briefly mention. It's called Sparse IR. And it has actually very good documentation. So if you are interested how to do that approach in practice and how to use the IR basis to do calculations, that's what I would recommend. There is also a tutorial and that we are currently putting together, which has things like how to do how to transform data from IR basis and back, how to do things like GW in that approach, how to do flex in that approach, how to do like Eliashberg equations, and how to do things like analytical continuations with that sort of approach. So there is a tutorial here, and I can then show you, maybe share the links or so to that. And yeah, so that's maybe the last thing I'm going to say.